So let's start calculus. We're going to learn about a concept of a limit. We're going to revisit a lot about slopes. So slopes of lines from grade 10 become super important. There's two types of calculus. This first unit is about differentiation, so we're doing differential calculus. Then our third unit in calculus is going to be integral calculus, and we're going to see how they're related to each other. Historical notes. Integral calculus is used to find areas under curves. So what happens with finding area is you develop a formula for area of a rectangle, an area of a formula, area formula for a triangle, and then a circle. And there's all sorts of shapes that you have formulas for. But then you get into some shapes like, what happens if I had the area under a parabola, or the area under a cubic function? Or how could I find the area under any kind of function? So then calculus becomes a way of figuring that out, and it's pretty cool. And that goes way back to some Greek mathematicians. One of them, Archimedes, originally called the father of calculus. An interesting thing is, I didn't know that Archimedes was a calculus kind of guy. When I knew he was sort of a mathematician thing, but we had to put a quote in our yearbook when we graduated, and my quote is an Archimedes quote. And then afterwards I've done some research in the university with Archimedes and stuff, so it's kind of interesting that I had that quote in my yearbook, because he did a lot of work with the lever. And the lever is basically, you can lift things by pushing down, or the door is a lever. And his quote was, "Give me a place to stand and I can move the world." Because if I have a lever long enough and I had a place to stand, I could lift the world up and down. Theoretically. Now, you can't actually do that. Don't try to do that. Or maybe you can feel like you're lifting the world if you can do a handstand. Anyways. Differential calculus. That's what we're doing, is looks at slopes, at tangents, at rates of change. How fast is something changing at a certain time? And it is, the discovery of it is given to Leibniz and Newton. Now, if you go by date, I think Newton's date is a little bit earlier than Leibniz's date. If you had studied any calculus in Europe and you had an English textbook, your English textbook would always say it was developed by Newton. Your German textbook would always say that it's developed by Leibniz. Even though the dates are different, it's not like they had social media back then where someone could post, "I discovered calculus, check it out." So they were discovered independently. So they have attributed the discovery, even though it was relatively the same time, independently by both of them. So they didn't have each other's help.
Newton was like stumped in like a physics problem because he didn't have the math skills to solve it, so he developed calculus to solve the physics problem.
Didn't have the math skills to solve it. Nice.
So he developed a new math.
So here is your average rate of change. All right, we talk about average rate of change all the time. If you drive to Portage and it's 50 kilometers away and it takes you an hour, what speed were you going? On average, 50 kilometers per hour. Now, that doesn't mean that every time you looked at your speedometer you were going 50 kilometers per hour, because nobody can do that on the way from here to Portage. You just start your vehicle and get to 50 kilometers an hour right away, and then don't stop or slow down for any red lights. And on the highway, you just stay at 50 while other people pass you, and they're like, "What is wrong with that guy?" But if it took you an hour to go 50 kilometers, your average rate of change would be 50 kilometers per hour. Calculus is more concerned at finding out what's happening at a certain moment. What's happening when you're on the highway right there? How fast are you going right there? Certain times, instantaneous rate of change, how fast you're going at a certain time, is important. The police are concerned with that, because when you pass them with your radar, if your instantaneous rate of change at that moment was 135, they're going to stop you. And even if you try to explain, well, I was stopped at a red light and I'm just trying to maintain an average of 50 kilometers per hour, they're still going to give you that ticket. So here we have a graph, and we would like to figure out over the following intervals, what is our average rate of change? So we can even think of this, as time and distance to sort of create a story to help us see this. From 1 to 3, can you see that you've gone up 6? Over a time period, if we're thinking of this as kilometers, you've gone 6 kilometers in a time period of 2. So what is our average rate of change, or our slope? It would be 6 over 2, which is 3. If our distance was kilometers and our time was hours, we would be traveling at 3 kilometers per hour, lightning speed. From 1 to 4, our distance hasn't changed. Even though we've gone somewhere and came back, we're now back to where we started. So even though it's happened over 3 hours, our average rate of change is 0 kilometers per hour. You could have accomplished the same thing by just not going anywhere. And then from 1 to 5, now you've gone down 6 over those 3 hours. So we get -2. Is it over 4 hours, sorry. Well, how can you go -1.5 kilometers per hour? Well, in this case, there's sort of a direction involved. So your change -6 meaning going backwards or forwards. Sometimes when we're talking about distances, because there's no backwards or forwards because you can go in any direction in 360 degrees, they just might choose one direction first, or they might actually include some sort of angle or direction to help you see where you're going. So that's average rate of change. Okay? Here we have another graph that's probably more realistic when you're traveling, that you don't have exactly straight lines, because if we were actually traveling along this last one, you're going the same speed, and then boom, at this point, you all of a sudden get hit by a baseball bat that you stop instantaneously and automatically start going back at another speed. This is very unlikely. More often when you slow down, you create a graph that looks more like this. And you've got round curves. Now, if you wanted to go from point A to point B, whatever the slope of that line would be, and you remember this formula from way back in grade 10, this is your rise over run formula. Whatever your slope of that line is the average rate of change from point A to point B. Sometimes along here, and this will be a key point that we do at calculus, can you see that if I would draw a tangent line at that point, the slope would be 0. That's the point where you've stopped, because you're changing directions. Even if you're stopped only for an instant. Same thing happens with gravity. You throw something up, there is an instant when it has to change from going up to coming down. At that instant, it's stopped. If we look along here, it looks like if I drew a tangent line right here, that looks like when I would have the slope to be the steepest. If we were talking about speed, that's when you would have been driving the fastest at that moment. So we start off just with looking at these average rate of change, and then we move towards instantaneous rates of change, and that's where our calculus will come in.